So this subject is near and dear to my heart. So that's what we're going to talk today. And we're going to talk about what machine learning is. I'm going to start off by telling you the very formalized version of machine learning, and then we're going to go into what it actually is. TechTarget says machine learning is a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed. Machine learning focuses on the development of computer programs that can teach themselves to grow and change when exposed to new data. That is fine. My personal, one of my favorite ways of teaching and favorite ways of learning too, is I feel that if I can't teach one of the topics that I'm learning to my 11-year-old daughter, then I don't personally understand it well enough myself. So that's why I came up with a much more simple explanation, which is in machine learning, the data determines the output. So that is the way I like to think about it. And so here I have a couple screenshots on a traditional kind of application. I have a little helper method on the left, and this is in Rails, and it's what helps generate if you ever have been on the dev camp side, it's what helps create those little left and right navigation icons. That's traditional programming. Machine learning is much different. Machine learning isn't you going in and explicitly telling the program this is what you're going to do at step 1, step 2, and step 3. Instead, what machine learning does is you don't know all the steps that are going to happen, and instead what you do is you actually feed data into the system, and then what comes out. And what happens here is instead of you having to feed the system at every stage, you're actually letting the data determine the behavior. So the example that I'm showing right here, and the reason why we have a big semi-truck and all these icons, is because this is actually time when I used Ruby and machine learning to build a machine learning integration, and it was for an energy company. And what we did is the fleet management system, or the company itself and the manager, he didn't know when the right time to retire one of the trucks was. They had all kinds of data. They had years worth of data on historical trends, on when a truck was when it was the right time to retire it in terms of knowing kind of after the fact. So they knew that after a truck has this many miles on it and it was driven by a driver who's a safe driver and it had received all of its maintenance, they kind of had an idea, but it was really just them guessing. And so what I built for them was a machine learning algorithm that could tell them, and it looked at all of the data that was coming in, and it would generate its own recommendations, and it would say, hey, this truck just hit these benchmarks, and so we think that it's a good time to retire the truck. Some practical applications of machine learning. Everyone here in this room is using machine learning in some form or another every single day. I gave you the example of fleet management. Every time that you have an email that goes into a spam folder, that's machine learning. Bank fraud, whenever you get a call and you hear that someone tried to use your credit card or anything like that, that was a machine learning algorithm that picked up on bank fraud. Medical diagnosis. Product recommendations. One of the earliest and most popular machine learning implementations was what Amazon and the early e-commerce companies did when they said, hey, we saw you like this product, we think you may also like these other products. That was a very early form of machine learning, and they have gotten very good at it through the years. Google search. It started off as a very simple indexing engine, grew into a massive machine learning algorithm, and I'll actually talk about some of the algorithms that they use in order to do that. So Ruby is not always known for its machine learning. I absolutely love Ruby. I think just about everyone in this room is a pretty big fan of Ruby. However, you usually don't hear the word Ruby and machine learning algorithms in the same sentence. Few reasons for that. One, in the very early days of Ruby, Ruby was not as fast as Python and some of these other languages. That is no longer the case. Ruby has definitely sped up over the years and now can handle large amounts of data like some of those other languages. So that's not really a reason, but it did have kind of that negative connotation years ago. Lack of libraries. Early on, this was also the case. If you look at some of the other popular languages like a Python or an R or one of those, they have all kinds of algorithm implementations and libraries that are available. Through the years, though, Ruby has gotten better at that, and I'm going to actually show you one of them when we do our live demo. The other reason, I still think this is one of the key reasons, is because Ruby is so good at running scripts and so good at being able to pass off its responsibility. I know a number of developers who, whenever they have a machine learning implementation they need to do, they'll actually go and they'll call something else. They'll call an R script, or they will call a C++ implementation or something like that, and they'll be able to have that script run it. So those are some of the reasons why you may not have always heard of that. However, hopefully I'll kind of change your mind after we're done today, because I'm going to show you how you can implement a machine learning algorithm in Ruby. So some of the popular algorithms, and you don't have to know a single thing about any of these, but I'm going to show you how you can walk through at least one of these today. And these just have some names such as decision tree, naive Bayes, k-means clustering. The names don't really matter right now, but all it goes to show is that when people talk about machine learning, there are a nearly countless number of implementations that you can use in order to do that. So there are going to be some times where a decision tree is a fantastic option to use. There's going to be other times where you might need to do something like k-means clustering. And the difference between these is the difference between supervised and unsupervised learning. So there's that really, but all algorithms for machine learning really can fall into one of these camps. Supervised learning is like when you, as a parent, go and you teach your toddler not to stick their finger or any other objects near an electrical outlet. That is supervised learning, because you go and you teach them that, and then as they grow older, they realize, based off of what you taught them, that, hey, that may not be a good idea to go stick that fork in that socket. Now, unsupervised learning is when you have a kid who happened to stick a fork in that socket and no one told them, but just their reaction. And if they randomly went and tested it out on a few other outlets and had the same response, they would sooner or later learn not to do that. That's the difference. So with a supervised algorithm, you as a developer creating the algorithm or implementing it, you're essentially giving some guidance to that algorithm. You're saying, these are some of the rules that you're going to want to follow, and then you still let the data, this is just the same amount of machine learning. You are just letting the data dictate the results. And the difference is with unsupervised, there you're letting all of the data go out. You're letting all the data run amok essentially in the algorithm, and then it does things like cluster it together, find ways of classifying it, and the unsupervised learning algorithms are typically harder to implement because you have to deal with a lot of data that's not as well organized, but it can be incredibly powerful. Also, this is one other difference before we get into the actual implementation. I need to mention the difference between continuous and discrete when it comes to machine learning. So we have two different types of learning. They're kind of algorithms, but more processes or data components. One is continuous data components, which this means, and we're going to, in the implementation, you'll see what this actually represents. Continuous are things that can be measured. So if you have a continuous algorithm or you have a continuous component in your algorithm, what you're going to be doing is you're going to be running the data through items that could be measured. This could be something like a user's height, a user's weight, the reviews of an Amazon product, anything like that. Now discrete is when you know the number of possibilities. So technically you could say continuous, you always know the number of possibilities because you say someone could be 1 inch to however many inches tall, but you're still having to measure it to get the data. Discrete are things like gender or the number of die or dots on a dice, that kind of thing. So you're going to see, I'm going to implement both of these in our demo and you'll be able to see what the difference actually is. Yeah, if that's what you're looking for, yeah. And I'll show in the, I think the demo, this is something that I had to do a ton of research for it to really kind of click in my mind, the difference between continuous and discrete. And it's a flag in the algorithm we're gonna put in. So you'll see the kind of the difference of it then. But yeah, there's a lot of overlap between the two. So I'm going to switch into the code. So we're going to implement two algorithms today. One is going to be a basic version of a decision tree. Both of them are going to be decision trees, but one of them is going to be a basic version of it, and the next one is going to be more advanced. This first algorithm we're going to implement is going to be a very basic version of a medical diagnosis system. So this is going to be something where we're able to pass in the data of a temperature and then a range on the temperature, and then we're going to say that person is sick or they're not sick or something in between that. And so this is going to kind of give us a base case for how this works. So the first thing we're going to do on the Ruby side is we're going to use the decision tree gem. And just so you can see exactly what this looks like. And I've included this in the show notes for you. So after you get this, I'll give it away to all of you. So decision tree. And I also want to give you a little bit of a walkthrough on the code implementation that he had to do in order to build this, because it's pretty impressive. So the first thing inside of the decision tree here is the attribute. So the thing that we're passing in is the temperature. And that is, as you can see, in all of this training data, that is what's available. Now, I have a very limited amount of training data, as you can see, but obviously in a machine learning environment, usually this would be something like a hospital record with 40 years worth of data passed into it. That's really where machine learning it becomes so strong, is when you have the ability to pass massive amounts of data into a system to help train the system. Because that's essentially what this does. And I named the variable training because that is exactly what we're doing to this decision tree, is we're training the system on how it should think. So from that point, we're just going to instantiate the tree. So I'm going to create a variable called decision tree and call the module. So it's going to be decision tree, and you don't have to worry about this next part unless you're really into machine learning, but we're going to be implementing the ID3 version of the algorithm. And we're going to pass in a few values. So we're going to pass in attributes, training data. We're going to pass in a default value as sick, and this is where we can see this continuous value. So we're going to pass in continuous as a symbol here, and what that's going to do is, like I mentioned earlier, this is going to show you that we're telling it it's a range here. So we're saying that this is not a discrete number of items. This could be something where the temperature could be 0 or the temperature could be 500 degrees. So it is a range that we're setting. What's that? The third param is a default one that is available, that he made available in the gem.
So basically, before you train it or whatever, it'll just return something.
Yeah, correct. Yeah. Now here, what we have to do is there is a train method, and we'll go through what this actually looks like in the gem code itself. And so we just call train on it, and what that's going to do is that is going to train the system. So it's going to run through the decision tree module, going to run it through the ID3 algorithm, and then it's going to train the whole system based off of the data. And if I run this right here, you can see that it creates a data structure of a struct, and it passes in some pretty interesting values. So right here you can see it creates a decision tree, sets an attribute as the temperature, then it also sets some other values such as the thresholds and some items like that. So it gives it kind of, if you look through every little line item of it, it does things like setting what the max is on dead as being the very worst item, and healthy as being on the top side of that. I'll clear the actual render. And so now what we can do is now we actually have to give it some test data. So all we're doing right here is we're just training the system. So we're training it so that it can learn, and then now that it's learned, then we can actually pass in our own value. So I can say test, and I don't mean test as in I'm testing to do anything. I'm saying that I'm testing to see if the values are, you see what this value is going to actually be. So if I pass in a value of 98.5 and healthy, I'm passing in healthy only to see, this would be kind of like if we're creating a medical diagnosis tool and we're comparing if what the doctor gave is accurate or if what the data gave is accurate. And after we run that, then we can call our decision tree, and then we can tell it to predict and pass in our value of test. And now if we run this, it's going to run through and it's going to tell us if our values are accurate. So right here we can see that we have our test data, which came in at 98.5, and it said that it was healthy. Now the cool thing about this is if you look through the training data here, we don't have anything that actually says 98.5. So if you were to, say you were to try to recreate this in Ruby just with regular code, you would have to create a full switch statement that goes through, or an if-else block that goes through and checks each one of these items. And that is technically not too hard with this kind of data set. I'm going to show you in the next example where it starts to get pretty crazy if you were to try to do that. But here we got the right value. So right here it shows that someone with a 98.5 degree temperature should be perfectly fine. Now if I clear this off, let's come down and let's look at what happens if I pass in someone who has a temperature of, let's see, let's go 100.6.4. If I hit save, and now if I run this, you can see that it predicts that that person should be dead. And it gives the diagnosis, obviously, that our doctor gave saying the person was healthy probably was not accurate. So this is the way that you could implement a very basic version of a decision tree.
Where should I get it from? Is it intelligently trying to draw some line in the middle, or?
That's where I wondered the same thing, and that's where I went into the gem code itself to see it. A lot of that comes down to in what you can see with the struct that's created, and notice the threshold items. It's in these, what I'm pretty sure are these threshold items is how a lot of that's being set. So you can see you have multiple thresholds like 101. Exactly. Yep. So it's a pretty neat system. So before we go in the advanced, I do want to take a quick look at the gem itself, because that is, we're going to skip that, because I think it is kind of cool to see exactly how he developed it. So scroll down, go into lib, and then go into the decision tree. And he only implemented the ID3 algorithm, but it works for pretty much most cases. You can see that he creates all of the different functions that we just called. So you notice when we called this train method right here, that is all defined here. So training takes data, it takes the attributes, and then it also takes in the default. And then from there, it simply goes through each item, iterates through a block, and then has the hash and grabs each one of those, and then creates if a one's not created, it creates a new one. So if you're wondering how each one of these things, let me run it again. If you're wondering how like these structs and all these threshold items are created, these are all happening at some point in the training stage for that. I really liked, so if I scroll down, I'm trying to see where he created this. Okay, yeah, so he has right here a graph implementation, which I thought was pretty cool, where he has a way of printing it and also defining some rule set. I don't believe he's worked on this one in a while, but Um, but I definitely recommend for you to go through it, especially spend time on the methods that we're calling, like predict right here. So predict takes the whole list in of each one of the premises and then goes through each one of these. So all the different logic and the things that you'd have to build in manually, notice how you can do that all just in a few lines of code right here. So, but this is what it would take to actually generate a full machine learning algorithm, and this is just one single one. So let me clear that, and I want to show you now a little bit more advanced version of this. Now, are there any questions on that before we go into the next one? Yeah.
Does it take the data that you provide and also kind of apply it? So if you were to like iterate, you would have a bunch.
Yes.
So it's constantly updating its own system.
Yeah. Well, yeah. I mean, the more if you added the 5,000 more items, you'd have a different set of rules that it lived by. Yeah.
So you're saying it feeds that data back into the tree?
Well, in this instance, yes, because we're just passing it all at one time. Yeah, if we were to be doing this in more of a real-time format where we're every day we're sending new data in and we're feeding it, a lot of it would kind of depend on how we're storing it, if we're caching any items to have some master data set it's comparing it by, or because if you have 10 million of these, you're not going to want to run that comparison every time. Oh, yeah. Oh no, go ahead.
I was just going to say, I was worried because in the instance that you want your training data set to be updated, right? I kind of want the records of like people that lived 30 years ago.
Right.
I'd rather have the records of people that lived
That
now and through the past, how many years ago.
that is what we're going to get into now. That's what I'm going to show you, because that was a really basic one, but you're 100% right. If you tried to treat someone who lived in the 1800s and could have had polio and who knows other things, they shouldn't be compared to someone who's there right now. So the next thing I'm going to show is actually how we can add an infinite number of variables and give weights to those. Correct. Yes. Yep.
Along those lines, so it's updating the ranges with
That one was not, but another implementation would. Yes. Looks like AirPlay decided to stop playing nicely. Okay, we're back. Okay, so yeah, the first implementation of that, it did not take that into consideration, but this one will. So this next one we have here is a little bit more advanced. I already loaded it up with some training data, and as you can see here, we have quite a few more parameters. My ideal scenario for this is saying that, say you're an advertising company or you are an e-commerce site, and you want to find who your ideal customer is. And let's pretend that you have your full historical list of data on all of your leads and customers. So right here we have data such as an age range. Then we have their education level. Then we have other parameters that could be, as you can see up top in attributes, this one is they're a high income or they're low income, if they're single or married, and then also if they purchase the product or not. So that's what the 0 and 1 there represent. So this kind of is going to show you how you can assign more values and let the data create you what the rules should be. First thing, once again, is we're going to pull in the decision tree. We have our attributes, like I already mentioned: age, education, income, and marital status. And for anyone, especially in the new students who are wondering how in a real world scenario you'd get access to this data, just think of this as being like a Rails database query. So you pulled a query in, this is kind of what your values are. That's if you're querying it, or it's just stored in a database. It could be stored in a CSV file. There's all kinds of different ways to do it. If you get to a spot where you have millions of records, then you're going to have to look into some of the more extreme ways of doing it, like with Hadoop or some of these other kind of large database structures. If you look at the way Facebook, for example, manages trillions of points of interest and that kind of thing, they don't have those all stored in a in a Postgres table or something. They have all kinds of different ways of getting creative on that side. So the cool thing is, so even though we have all these other parameters, let's pretend that you had built a series of if-else statements in the previous one, because you could have easily recreated that other system with a bunch of if-else and check to see, is this person sick or not, just based off of ranges. Let's say that I told you, okay, that was awesome. Now I'm going to hand you all of this data right here, and I want you to find who an ideal customer is for us. That would be a much more complex set of if-else statements, because if you had to take in all of these items and be able to check on each one of these, you're going to have to write a decent amount of code. The cool thing that I like about this is you might notice something familiar about what we're going to do here. Notice here also, last time I used discrete, here, or last time I used continuous, now I'm passing this in as a discrete. Remember that the difference is continuous is something that is usually on a range and that we're using to measure. Discrete is something that we usually have a limited number of items. So last time we were looking at temperatures. Here, we're looking at a set of pretty kind of formalized kind of data in the sense of, we have age ranges and we have a set number of each one of these items. Now we're calling train on it, and just to make sure that I haven't made any syntax errors or anything like that, we will run this. And everything looks like it's working so far. So we have our decision tree, and it created that decision tree for us. Clear that off, and now let's actually pass in some data for it. So I need to pass our test data. So here I'm going to create an array of strings. I'm going to pass in 18 to 35. I'm going to say that this person is a PhD, high income, and they are married. And then from there, I'm going to say decision tree predict, pass in test. And now if I run this, you can see that it is saying that this person should be a customer. This person is very likely a customer, and that's where, if you look on the very last line, that is what that 1 stands for, that 1 represents. So let's go through exactly how it came up with that recommendation. So it looked first at all the ages. Then it looked at all of the different options. We only had 1 PhD, so it wasn't exactly a ton of data for it to look at. Then it looked at what type of income, low, high, anything there, married, and if they're a customer or not. So what this is essentially doing is we're providing some more intelligence for the system. So instead of just saying, here are 2 parameters, like temperature and if they're sick or not, here we're saying that we actually want you as an algorithm to go through and pick out all of the different kinds of values and for you to essentially assign those weights. Remember I said at the very beginning how the machine learning algorithms, one of the biggest keys to them is that the data predicts the end result. And that's exactly what it's doing here. As you notice, I didn't do anything to influence what type of customer should be the ideal customer. All I did was provided all the historicals, and then I let the system generate all of that. So here, to get back to answering your question from earlier, what I would do on that side, if I was building some type of medical diagnosis engine and I had data for the last 100 years, I would simply assign different types of values here that would say, this person is has been born within this age range or something like that, and then it would then compare that with the test data. So in other words, I would pass in all the parameters to try to make the person we're testing, the person we're trying to diagnose, and add in those parameters, kind of like we did right here with age. And by doing that, then all of a sudden they're going to be judged from a diagnosis standpoint right alongside of everyone in their age bracket. And that way, that is all of a sudden a point of weight. Yes?
How hard would it be to change that surviving between 0 and 1, or it comes out 0.89, or you only pass a partial information? Probably wouldn't use like robust and like a secure knowledge of what it is.
Absolutely, yeah. That's a great question, and that gets to one of the most challenging things that machine learning developers have to work against is usually the data you're getting is not always perfect. You usually don't have a nice array like this. In fact, Eric and I just had this conversation just a couple of days ago on trying to build a machine learning algorithm, and there was all kinds of data missing in different points. Part of it comes down to cleaning. So usually what you do is build some type of kind of pre-processing script that goes through and cleans it to match it up as well as possible. And that's actually an entire branch of study in machine learning, is how to clean data so that it can be used and piped into something like this. Now that also, your question also kind of touches on right here. This is more of a form, a little bit of a supervised learning algorithm. We're structuring the data at least in a way where we have things like attributes and education. So we're giving it a little bit of education. Decision trees are more of a form of supervised, whereas take, for example, creating a spam filter. Spam filters usually use what's called it was the second algorithm that I listed, the naive Bayes algorithm. That is an unsupervised learning algorithm, and with that one, you can pipe any data you want into it. It doesn't care about anything. All it does is it goes through and it starts to find predictive ways of seeing what items pop up more than other ones. So, for example, with spam, in the early days, I'm not sure age-wise, how I am age-wise here, but I remember early on, my entire inbox was always filled with spam. I mean, there was no kind of way around it. I had a spam folder that would get like one thing, and then the 90% would go in the inbox. Through the years, though, the company started to develop better machine learning algorithms, and they started to predict. They would see certain words like Viagra. All of a sudden, those started all getting piped right into the spam filter. It was because of the machine learning algorithms. They were picking up on that and predicting that, hey, this is probably something that somebody doesn't want. That's why in the very early days, it was so important for you to go and click spam on an item, because that would start to give weight to which type of email was considered spam versus which ones you actually wanted to keep in your inbox. The systems have gotten so good now that they don't really look at that a ton. Now they really care more about some of the things they put in the background. Another great example, and it's a reason why I wanted to talk about naive Bayes and why I listed it there. If you talk to a developer on the machine learning side at Google, they will tell you Google uses naive Bayes all over the place. They use it for Gmail for spam filtering. They use it for different parts of the search engine. That's how it knows when you start typing a few words and you see how it does autocorrect. That is a machine learning algorithm. It's picking up that you said X, Y, and Z, and so it thought that based off of all of our knowledge on the past week, then we think that this is what you're searching for. That's how you can start typing something in, like back in the Olympics, and you could start typing something in and it would pull up all Olympic related items, and it was because their machine learning algorithms were constantly looking and trying to predict what people were going to be searching for. And that is everything on the demo side. I also, in addition to recording this, I also created a spot where I posted all of this code. And let me actually pull this up for everybody. If you want to go, I create a bit.ly link to it. If you want to go to that, and I'm not sure, do you distribute the links or anything? Okay, so Isaac will distribute all of this, but if you do want to go to it, I placed on my blog all of the code that I just talked about.
You can send like links.
Yes, I will do that.